So there are three parts, A, B, and C. Usually before I used to solve part A, but now I decided to solve part B. But in your homework, of course, you're going to have all three parts. Right? So what do we have here? A circular loop. Where is my circular loop? Here. A radius is given. And usually we use R capital to show the radius of this circle, right? But R capital is usually more often used to denote the resistance. So we're going to use R sub 0 to denote radius of the loop. So we have a conducting circular loop. Conducting circular loop. And R naught, its a radius, is, okay, I don't remember the number. What's the number? 10 centimeters in diameter, so 5 centimeters in the radius, right? So 5 centimeters. Or let me convert immediately, 5 times 10 to the power of minus 2 meters, right? Then resistance is also given, 0.2 ohms. It's a typical resistance for a piece of wire. So R equals 0.2 ohms, right? Let me close this bracket. Then what else is given? Yeah. Okay, let me draw the picture now. And I use my takeout containers to draw these pictures, right? So let me do it. So that's my loop. All right. This is R naught radius. And the whole thing is exposed to a uniform magnetic field. Direction, let me, in part B, dot. Dot, it means out. Right, let me use blue. So to show these dots, so this is our external magnetic field. So that's B external, right? And that's it. Yeah. We also know that magnetic field dB external over dt, we know the rate of change of the external magnetic field. And the rate of change is 0.5 Tesla per seconds. Okay, upstairs we have Tesla, downstairs seconds. Tesla per seconds. And in part B, this magnetic field is decreasing. So, decreasing. Okay, let me abbreviate. Decrease. Okay, and the same question like here. Can we find the value of the induced current and its direction? So, let's find I induced. Again, we have a loop exposed to the magnetic field. And if magnetic flux is changing, then again, according to the Faraday's law, there will be EMF, induced EMF and induced current. So direct application of the Faraday's law, right? So, and again, we're going to divide that application into two steps. We can apply Lenz's rule, and then we can find absolute value of EMF and then the value of the current, right? So again, we will apply Faraday's law, d phi over dt, right? And then again, two steps. So the first one, okay, I will just use the bullet. So let's find direction, right? It doesn't matter. Direction. Lenz's rule. Again, three parameters: BA theta, B external area, and the angle. And so let's analyze. And let me start again from, okay, in the middle, area. Area of the loop stays the same. Area is constant. Angle, Okay, let me pick area vector, direction of the area vector. And again, I will pick it in the direction of the external magnetic field. So area vector will be represented by this dot. So it means in the direction of the external magnetic field. So in this case, theta is 0 degrees, and anyway, it's constant. But external magnetic field, since it is decreasing, given, so we can write this. Oh, we can draw. So it's going down. So as a result, I can come up with a conclusion about the magnetic flux. So it is going down. So flux is dying. Loop doesn't like it. It will wake up immediately and start doing something. In this case, it will start behaving. Behaving like Florence Nightingale again. It becomes supportive, right? So supportive, it means it will start driving current in such a direction so that the induced magnetic field will be in the same direction as the direction of the external magnetic field within the loop. So I can write, so B induced will be in the same direction as B external. Again, within the loop, let me emphasize that. Within the loop. Loop. Right, within the loop. And so now let me draw that dots or crosses representing this induced magnetic field. So the same direction. So within the loop, I have to draw a few dots. So these are my B induced. Dots representing induced magnetic field. Right. Feels like there must be another one here. Okay, it's better. Right. Okay, and now the last step, right-hand rule. Where is my loop? Here. So dots means out of the board, right? So it means that magnetic field, induced magnetic field this way. Again, cup is here. So in order to match that direction, I have to position my fingers like this, right? Directions are the same. And my thumb gives me direction of the induced current counterclockwise. Counterclockwise direction. Let me check if I'm getting, if I'm getting the correct direction. So, so this will be my I induced direction. So I induced. And so I can write here. So I induced CCW. So that's first part of the problem. In part A, actually, it's pretty much the same, but this rate of change, the flux, not the flux, external magnetic field is increasing. Right, so you will have to repeat something similar, but of course, conclusion can be different. But again, it's not over. So we need to find the value of the current, and basically it means that first we need to find the value of EMF. We just need to look at this absolute value of the rate of change, right? And sort of similar to this. So first of all, let's write explicitly magnetic flux. Expression for the magnetic flux, again, my explanation box. A magnetic flux equals, again, B, and again, it's an external B dotted with A. Since I pick area vector and the angle is 0 degrees, so it will be cosine of 0 degrees over there, BA cosine of 0 degrees, so it will just give us B external A. Cosine of 0 degrees is 1, so it will be B external times A, right? So let me close this explanation. And of course, minus I will drop. It will be D over dt, B external times A. And now look carefully at both of these quantities. Which one is constant? Over here, what was the constant quantity B? As a result, we extracted it from the sign of differentiation, actually extracted it from the sign of absolute value, because these are magnitudes. Magnitudes can be only positive. So now look carefully in this case. B external is no longer constant. It changes in time or with time, but area, yeah, area stays the same. So area is constant. We can extract it from the whole thing, right? So it will be A, and absolute value of dB external over dt, right? Area, can we find area? It's a circle. Radius is given, r naught. So pi r naught squared, right? Pi r sub 0 squared and dB external over dt. And dB over dt is given 0.5 Tesla per second, right? So let me emphasize on that. So let me just draw some line connecting. Okay. And so now you can, of course, plug numbers. Radius is in meters already, so I'm not going to plug. I will just write down the answer immediately. So it will be with 3 sig figs times 10 to the power of minus 3 volts. So almost like 4 millivolts, right? Not that much, but enough to drive some current. But again, it's not over. We need to find a value of induced current. So the last step, I induced, of course, EMF we just found, and resistance of the loop is given. In this case, we don't have to make any assumptions. Resistance will be the same all the time, right? Because we don't change the size of the loop like we did in this case, right? In this case, I had to write, let's assume that we know the resistance at this particular moment of time. But in this case, yeah, resistance will be exactly the same all the time. So anyway, so if you plug resistance is given, you will end up with 20 milliamps. All right, 2 times 10 to the power of minus 2 amps, which is 20 milliamps.